Here's an example where we'll combine both moments and forces to figure out what's going to happen with this gate here that's hanging from a hinge up above and is keeping this water behind it from flowing out over to this side. So if there was no force holding this gate in place, it would tend to swing out and the water would pour out the bottom down here. So we're definitely going to need a force down here at location B. I'll call that F sub B because it's at location B here. And we'll need some force up here at location A. And if it's hinged up here at A, we'll need to account for moments about the hinge. And it'll be easiest to calculate our moments about one of the locations where we know one of these forces is applied, because then we'll only have to account for one of these forces in our moment equation. It'll just make the problem a little simpler. So the things we know, the sum of the moments about A must be equal to 0. And in this case, I'm going to look at the clockwise moments about A. Doesn't matter whether we pick clockwise or counterclockwise, as long as we do the same thing throughout the whole problem. So by saying that the sum of the moments about A must be equal to 0, then FA is going to have no moment because it's acting right at A, so there's no moment arm. And FB is going to produce a moment in the clockwise direction, and it's got a moment arm of 5 meters, so that's quite a distance. So we'll wind up with 5 times FB plus 0 times FA being equal to the integral over the region of interest, and that's this zone in here, of the distance r times PdA. And we're going to neglect atmospheric pressure. We're going to do everything in gauge pressure the way we usually do. So if I rearrange that, I'll wind up with FB, and I can solve directly, as I did in the last example. I can get FB equal to, well, there's going to be a rho g involved. 5, we're going to divide through because that was the multiplier on the other side. And then our integral will be 5 minus y. Well, where's our y dimension? Let's put it down here. So if that's y, then the radius will be 5 minus our motion in the y direction. So that's r. Our pressure will be rho g times the depth under the water. That will be 2 minus y. So rho g times 2 minus y. And dA will be w dy. We're going to work with water at 998 kilograms per cubic meter. And we're going to assume that the width into the paper here is 1 meter. So that'll make our lives a little easier. The W will just disappear. And the region that we're going to integrate over, well, we have to go from y equals 0 to y equal 2 because that's where the water is applying the pressure here. So y equals 0 up to y equal to 2. If I carry that through, I'll wind up with rho g over 5, integral 0 to 2. Then doing the multiplication, 5 times 2 is 10. Negative y times 2 is 2. Negative y times 5 is 5y. So combined we'll get negative 7y plus y squared dy. If I do that integration, rho g over 5, and the integral of 10 is 10y. The integral of 7y is 7 over 2y squared, and the negative sign stays. The integral of y squared is y cubed over 3, and I'm evaluating those at 0 and 2. So if I plug that in, along with 998 and 9.81 for rho and g, and do the calculation, I'll wind up with 17.0 times 10 to the third, or 17.0 kilonewtons. That's a very large force, certainly if we were trying to hold back the gate ourselves. Now, I've applied the moment just as I did in a previous one, and I was able to find out what FB is, but I can also now find out what force we need on that hinge to hold the top part of the gate. So this is completing the problem. I've got a gate with both moments and forces, and I can use that to solve the complete set of forces that need to be applied here. So by saying not only are the sum of the moments equal to 0, but the sum of the forces in the x direction must be equal to 0, then I'll wind up with Fa equal to the pressure force, just the rho g, integral 0 to 2 as we had before, but this time I'm only looking at pressure times area. So 2 minus y, the pressure, times rho g, times dy. That's the Fa, and it's equal to that force minus whatever force we already had from B, minus Fb. So a simple force balance on a free body diagram. And if I carry out that integral, that'll be rho g times 2y minus y squared over 2, evaluated at 0 and 2, minus Fb. I know Fb is 17 kilonewtons because I calculated it up here. I can plug that in. I know density and gravity from over here. And I'm going to have y equal to 0 and y equal to 2. And when I plug it in, I get Fa equal to 2.6 kilonewtons. So what this is telling me is that the vast majority of the force that we need in order to hold back this gate and keep the water from flowing out and pushing the gate aside, the vast majority of the force is down here at location B. Fb is going to be 17 kilonewtons, while Fa is only going to be 2.6 kilonewtons. Given that result, that will tell me now roughly how strong do I have to design this hinge system to be, and what sort of an actuator do I have to put down here in order to be able to operate this gate to allow water to flow out or to be able to push it closed again when I want to stop the water flow. So this is practical design applications of fluid statics. And we've balanced out to find out the full set of forces on that gate by looking at both a sum of the moments so that it doesn't move and a sum of the forces.